In our last section, we talked about annuities in terms of an investment or a savings plan where regular deposits are made. But annuity can also represent a payout, such as a lottery prize, a structured settlement from a lawsuit, or even a retirement fund. Let's look at this kind of annuity. Before we start examples, we have a formula that we need to look at. So if X is a non-zero real number, and N is a positive integer, we know that x to the minus 1 plus x to the minus 2 plus x to the minus 3 all the way up to x to the minus n is equal to 1 minus x to the minus n over x minus 1. And we'll be using this formula as a shortcut. Now we'll be talking about the present value of an annuity. It means how much do I need today to be able to make payouts of the amount that I want for the number of months that I want. Okay? And our formula for this present value looks like this. The present value is equal to the payment, the amount we're paying out, times 1 minus 1 plus I to the negative n power over I, or we could say it's important not to confuse this formula for the present value with a formula for an annuity's future value. So in this one, the numerator is 1 minus 1 plus I to the negative n power. It's important not to confuse this formula with a formula for future value. In the future value formula, the numerator looks like this. 1 plus I to the positive n minus 1. Let's work an example now. Camilla was in an auto accident. She sued the person at fault and was awarded a structured settlement in which an insurance company will pay her $2,000 at the end of each month for 7 years. How much money should the insurance company invest now at 4.7% compounded monthly to guarantee that all payments can be made? Okay, let's write down some important facts. They're going to pay her $2,000 per month, 7 years. So real quick, 7 years is equal to 84 months. So they're going to have to make 84 payments. And they can make 4.7% compounded monthly. So how much money do they need to set aside so that they can make all these 84 payments? So we're going to look first at the present value is equal to PMT, payment, and 1 minus 1 plus I to the negative m over I. So let's substitute what we know, 2,000, 1 minus 1 plus 4.7%, so 0.047, except that's annual, so 47 divided by 12 to the negative 84 over 0.047 divided by 12, and this comes out to $142,000, $924.79. Okay, so if you think about $2,000 for 84 months, that was going to be quite a bit more like $168,000. So by using the interest, they can reduce the amount they have to set aside now and just make the payments over time. Pause the video now and work on checkpoint 1. Another example of this kind of annuity is money that's paid out from a retirement fund. Let's look at this. To supplement his pension in the early years of his retirement, Hong plans to use $400,000 of his savings as an ordinary annuity that will make monthly payments to him for 20 years. If the interest rate is 5.2%, how much will each payment be? So we know Hong is starting with $400,000, and he wants to make payments for 20 years, monthly payments, so that's 240 payments. And his interest rate is 5.2%, or for calculation, 0.052. And we want to know now how much is he going to get. So we'll start with the present value, 400,000. We don't know what the payment is. That's what we're trying to find out. And we got 1 minus 1 plus. Our interest rate is 0.052 over 12 to the negative 240th power over 0.052 over 12. Okay, and then at this point, it really is just a calculator problem. Work all of this out first and put it underneath the $400,000. And we get a payment of $2,684.22. So this is how much he'll get per month for the first 20 years that he's retired. Pause the video now and work on checkpoint 2. Some kinds of loans can also be considered as annuities by the person who loans the money or the institution. For instance, a a loan that's set up to pay for a car, where the payment is set, same amount every month over a definite term, can be thought of as an annuity. For instance, in October 2016, Chase Bank advertised a used car auto loan rate of 2.84% for a 5-year loan. Shelley wants to buy a used car for $18,700. Find the amount of each payment. Okay, so we know that the interest, 2.84%, so 0.0284. It's a 5-year loan. So we're going to have 60 payments. And our present value is $18,700. And we want to find the amount for each payment. So we'll start with 18,700 is equal to the payment times 1 minus 1 plus my interest rate, 0.0284 over 12 to the negative 60 over 0.0284 divided by 12. Once again, we're going to calculate this and put it under the price of the car. And this comes out to $334.69. Pause the video now and work on checkpoint 3. Another kind of loan repayment that's considered an annuity is called an amortization, and this is usually used in the context of purchasing a home. We're going to manipulate our formula a little bit to make it a little less cumbersome to work with. If I need to know the payment, I can write the payment as present value over 1 minus 1 plus I to the negative n over I and to simplify this, since I have this divided by another fraction, I'm going to just move the I up to the top. And now it's a little simpler to look at. Okay, let's look at an example. On October 10, 2016, the average rate for a 30-year fixed mortgage was 3.37%. So I'm going to write that down, 0.0337, and we're going to go with a 30-year mortgage, making monthly payments, so 360 payments altogether. And the price of the home was $285,000. But the purchasers paid 20% down, so they're only going to get a mortgage for 80% of the selling price. So we want to find the monthly payment needed to amortize the loan. Well, let's do some simple calculations here. $285,000 times 0.8 gives us $228,000. And now we can put numbers into our formula. So we're going to start with $28,000 times our interest rate, 0.0337 over 12, divided by 1 minus the quantity 1 plus 0.0337 over 12 to the negative 360th power. And this gives us a payment of $1,007.35 for this mortgage. Now, we want to find out, after 10 years, approximately how much is still owed on this mortgage. Okay, so we've made payments for 10 years. How much have we actually paid off? Okay, so we're going to start all over with present value. Our present value is equal to $1,007.35 times 1 minus 1 plus 0.0337 over 12 to the negative 240. Okay, I've made 10 years worth of payments, so 120 payments, 240 left. 0.0337 over 12. And this comes out to $175,710.23. So this is the remaining balance, which when we started with $228,000, we've only paid off a little more than $50,000 in the first 10 years. Okay, this shocks a lot of people when they get involved with a mortgage, that at the beginning of the mortgage, you're mostly paying interest and you're not paying off your loan to a real significant extent. But the idea is that every month you're paying off a little bit more, so that at the end of the mortgage, almost all of the payment is going toward the principal and very little toward the interest. But at the beginning of the mortgage, it's just the opposite. We have a formula for remaining balance, which might make this a little bit simpler. My balance is equal to payment one minus 1 plus the interest rate to the negative n minus x power, where n is the original number of payments and x is the number of payments I've made, over I. And this is an approximation, but it will get you pretty close. Okay, for checkpoint 4, you're going to do this calculation again, and this time see what the balance is after 15 years of payments, or halfway through the mortgage. Pause the video now and work on that. The formula that we just looked at is a good way to get a quick approximation, but for banks and businesses, it's not really accurate enough. To get accurate numbers, they use something called an amortization table. I'm going to show you how to do that on a spreadsheet program in just a bit, but let's look at an example first. Beth Hill borrows $1,000 for 1 year at 12% annual interest, compounded monthly. Find her monthly payment. So we're going to use the amortization payment formula. My present value is $1,000. N is 12. I'm going to pay it off in a year. And the monthly interest rate, I over N, is going to be 12% divided by 12 months, or 0.01. So her payment is equal to PVI over 1 minus 1 plus I to the negative n power, or 1,000 times 0.01 over 1 minus 1.01 to the negative 12 power. And this gets us a payment of $88.85. Okay, as often happens with a small loan like this, it doesn't always get paid all the way down to zero before something changes. So after making 5 payments, Beth decides to pay off the remaining balance. Approximately how much must she pay? So what's her balance after 5 payments? So we're going to apply the remaining balance formula. Remember, PMT is the $88.85. I is 0.01. And N minus X would be 12 minus 5, so 7. So her approximate remaining balance is 88.85 times 1 minus 1 plus 0.01 to the negative 7th power over 0.01, and her payoff amount is $597.80. Okay. Normally on a loan like this, we wouldn't bother to construct an amortization table, but we will do that for this example just to start with a simple table before we try one for a mortgage. And I'll be showing you how to do that with an Excel spreadsheet. Part C asks us to construct an amortization table for Beth's loan. Normally I wouldn't do a table for a loan this small, but this is a way to learn how to make the table without getting into a big complicated one, which we will do in our next example. I'm using Microsoft Excel, but you can use any spreadsheet software to construct this table. Let's start with the column headings. The first one is the payment number. And then the next column would be the amount of the payment. I'll make these a little bigger so they're easier to read. And we'll drag down the cell so they fit better. My third column is for the interest for the period. And then next to that, the portion that goes to principal. When I make a payment on a mortgage, the interest for the month is paid first, and then whatever happens to be left is applied to the principal. And then my last column is the principal at the end of the period. Make this just a little bit bigger so it all fits. And I start my payment with payment number 0. This is going to represent my loan at the beginning of the loan. So I want to make my numbers a little bit bigger also so you can see them. This is not necessary if you're just doing this for yourself. So for payment number 0, we figured out in Part A that our payment should be $88.85. So that's there. I'm not paying any interest in this period. In period 0, I'm not making a payment, so I just enter a 0 there. Nor am I paying any interest or principal. The only reason this line is here so that we have the principal at the end of the period, which is the entire amount of the loan, $1,000. Now we'll go on to the first month, and this is when we make payment number 1. Part A told us that we were going to pay $88.85 every month. And then our interest for the period, we're paying 12% per year, so the percentage per month is 1%. So we just take 1% of what the principal was, and that's our interest payment. So in this case, it would be $10. Well, if $10 is applied to the interest, everything left of the $88.85 is applied to the principal. So we enter here $78, here $78.85. That's how much is applied to the principal. And then in this box, we're going to do a calculation. I could take $78.85 and subtract it from 100, but I want to use a formula so that I can repeat it every month. So we're going to start with equals, and then parentheses. And I'm going to start with the principal from the previous month. And you see here it gives me the cell designation for that. And I'm going to subtract the amount that was applied to the principal in this month. And there's my balance, $921.15. Now what this allows us to do is to not enter each line by hand. Starting with the payment number, I can put in a 2 or maybe even a 3. But now I've given the spreadsheet an idea of how this column should progress. So I can just hover over this lower right hand corner and drag it down until I get the number of payments that I need. So that fills up with the number of payments. I can do something similar with this. I'm not going to highlight the 0 because I don't want this to change. So if I only have one number, it's just going to repeat that number. So there's all my payments. This one, I put in 10, and I really should have put in the 0.01 times this number. So let's change that. This is going to equal 0.01. I can use a constant for that because it doesn't change. I pay 1% every month. And then I'm going to multiply that by whatever the principal was at the end of the last period. And that's why we needed this number here. That's why we had to have a payment number 0. And it looks the same, but now this is a calculation. So when I drag it down, it's going to make that same calculation in every cell. And you see, most of the time it ends up being 0 because I don't have any principals here. Now don't worry about it, it will fill up. Okay, this is already set up as a calculation. No, it isn't. I need to set it up as a calculation and say this is equals this amount minus this amount. The amount of the payment, take away the interest. And again, it looks the same, but now it's a calculation. So now I'm going to drag that down. And because this is saying there was no interest, it's saying the whole payment is going to be applied. When I change this principal at the end of the period, this will change as well. So now this is a calculation, and I can just drag it down, and we'll do the same calculation with new numbers. And so I can see the balance, and the balance we found after 5 payments was $597.80, and this is $597, and it would round up to 79. So it's a penny off, but it's very close. So I look down now at my last row, and I see that my ending balance is minus 1.5 cents. So I don't want to overpay, so I'm going to change this last payment instead of $88.85 and make it $88.84. Okay. Often on a loan, the last payment is slightly smaller or slightly larger to make the balance come out exactly even. So now I'm still a half cent to the negative, but if I were to change this to, say, $88.83, then I would have a balance still. So I need to leave it at $88.84. And that is an amortization table. Example 6 asks us to do some more work with example 4's mortgage. And so we're going to use a similar amortization table to figure that out. I'm going to use the same headings and change the beginning amounts. The mortgage was originally $228,000. So I put that there. I know it was a 30-year mortgage, so I'm going to want to add quite a few lines here. So I'm going to come down this way, if it will let me. And we're scheduled to make 360 payments, so I need 361 lines, since I have one for my heading. And I'm going to make those somewhat higher. And then I can take just the last few numbers here and drag this down to get my 360 payments. And I think you can see here that having a table can be much more useful for a long-term loan like this. Okay, our original payment was $1,007.35, but we're going to make an extra 1/12 of a payment every month, which is an extra $83.95. So now our payment is $1,091.30. And again, I'm going to drag this down. And if I get a little bit short, I can just drag it down again. Okay, our interest was 3.37%. So for this part, I need to replace the 0.01 with 0.0337. And I'm going to drag that down. Now I do need to make an adjustment because the 0.0337 is the annual interest rate. And so we're going to divide this whole amount by 12 to get the monthly interest rate. A lot more reasonable. And once again, our portion for the principal, actually we can leave this the same. It's still B3 minus C3 because we've changed these amounts and that makes this change. But we can see that we need to add a lot more payments on here. So I'm just going to click this last one and drag it down. And we saw early on that our portion for the principal was in the 400s. As the mortgage goes on, it's going to be a lot higher than that. But it's not going to be 1091. Remember, the table's not going to be accurate until all the columns have been adjusted. So now I'm going to do this last column. And now we see that there's quite a few negative numbers here. Negative numbers in this balance column mean that we've overpaid. We've paid beyond what we owe. So we're looking here. This is the last positive number at payment number 315. So if there were a total of 360 payments, we've just chopped off 45 payments off of our mortgage. Okay, so you can see that just making one extra payment a year saves you nearly 4 years off your mortgage. Shortens it by 4 years. And now we want to see the amount of interest that's saved. So we're going to look at the payment. The new payment was $1091.30. And we made 315 of those payments instead of 360. So I can do a quick little calculation out here. Equals 1091.30 times 315 payments. And blow that up a little bit. And we see now that we have $343,000, $343,759.50. Okay, our amortization table shows us that we can save almost 4 years off the time of a mortgage by paying that extra 1/12 of a payment every month, which amounts to paying 13 payments a year. For many people who are on a bi-weekly pay schedule, this is a real good way to pay off your mortgage faster, because if you just pay half a payment on every paycheck, you'll get that extra payment in there every year. But now we want to know, how much money did we actually save by paying off the mortgage early? So going back to example 4, our total of payments was $362,646. But with the extra payment, we only paid $343,865.51. So what we saved ended up being $18,780.49. This is money that was not paid to the bank or the mortgage company as interest on the loan. So just that extra 1/12 of a payment, in this case it wasn't even $100, saved us $18,000 over the life of the mortgage. Pause the video now and work on checkpoint 5. In our last example for this section, we're going to look at the difference in payments on lottery winnings, whether you take the lump sum or annual payments over a period of years. To do this, we need to look at a new formula, and it's this. This is a formula for an annuity due. So basically, this on the end is the present value of an annuity due that's made in n-1 payments. Okay, and the payments are made at the beginning of each period. Start with one payment, and these are the following annual payments after that first one. Okay, and here's our problem. The Illinois Lottery Winners Handbook discusses the options of how to receive the winnings for a $1 million scratch ticket. One option is to take 20 annual payments of approximately $50,000, which is 1 million divided into 20 equal parts. The other option is to take a lump sum payment, which is often called the cash value. If the Illinois Lottery Commission can earn 4.22% annual interest, how much is that cash value? Basically, if you take the lump sum, it's going to be less, because if you let the Lottery Commission keep the lump sum, they'll invest it and make some money on it. So let's work this out with this formula. So our present value is equal to our payment, which would be $50,000, plus the $50,000 times 1 minus $1 plus 0.0422. This is the interest they can earn on the money to the negative 19 and minus 1 payments over 0.0422. And so this comes out to $694,593.49. So if you take the lump sum, you're going to get less than 70% of the money, because the lottery commission could have invested that money to earn some money. But the good news is you could invest some of that money too and get back some of yours. Okay, pause the video now and work on the last checkpoint, and then you'll be ready to go on to your homework assignment.